Today we're going to talk about higher order derivatives. Higher order derivatives, what we're going to talk about is if a function is differentiable, then we can find its derivative. And we've been doing that in class for the past several days, couple weeks. But if we want to find the derivative of a derivative, then what we're doing is we're finding a higher order derivative of a function. So if you find a derivative of a derivative, then what you've found is something called a second derivative. The second derivative of f of x. If you take that second derivative of x and you find the derivative of that, then you've found the third derivative. So if you find a derivative of the second derivative, you've found the third derivative. Say that again. And you can keep on taking derivatives for as long as you want. Sometimes they're never ending, and sometimes they do end. Let me talk about the notation. First of all, the first derivative is what we've been finding for several days. The first derivative, we have called that f prime of x. We have called that y prime. And sometimes we've called it dy over dx, which is the change in y with respect to the variable x. Or sometimes it would be dy dt. It depends on what the variable is. But if the variable is x, you're taking a derivative with respect to x. So this value, or this variable right here, has to match this variable right here. The second derivative has a notation like this. You put two little apostrophes here. This is called f double prime of x, because sometimes we'll call this f prime of x. I think we've talked about that, that wording before. F prime of x. Hopefully you've heard me say that before, but if not, that's also called f prime. So if you're taking a second derivative, you can call that y with two little quotation marks. And when you write dy dx, what you do is you write a little 2 between the d and the y, and then you write a 2 after the x. So what we say is d squared y over dx squared. And all that means is the second derivative. And like I said, this is called f double prime. Sometimes you call it f double prime of x. The third derivative, you can probably guess what that looks like. The third derivative has an f with 3 quotes in it, f triple prime of x, and then the y has 3 quotes. And if you want to write it as dy dx, it would be d, and then you have d3y over dx to the third. So you can call that f triple prime. Once you get to the fourth derivative, though, you kind of run out of room to put the primes in there. You don't put like 4 little primes because it would sometimes get hard to count if you're taking like the 7th or 8th derivative. You don't want to count all those little quotation or those little apostrophes. So what you're going to do is you're going to put a F, and then there's going to be a little 4 here, and usually you'll put a little parentheses around that, which means don't take the function to the 4th power. We're actually finding the 4th derivative of the function, f of x. And then if you wanted to write it as y, you can put a little quotation or a little parentheses y4, and then that would be d4 of y over dx4. And then you can continue and take the 5th, 6th, 7th derivative, but in the end, if you want to find the nth derivative, like the 8th derivative or whatever, however long you have to take them, the nth derivative, the notation is f, and then you put the little n in parentheses like you did with the 4x, and that's y parentheses n, which is d n of y over dxn. So that's just some notation. And now what we're going to do is we're going to do some examples so you can get a feel for what the derivatives might look like. So for example, let's say we have, we'll call it f of x. Let's say f of x is equal to 1 over x. Well, what's the derivative of that? F prime of x. Hopefully you know that we're going to change this, and how you would change this is you would call this x to the negative 1 power, so you can take the derivative a little bit easier than using the quotient rule. So the first derivative is equal to negative 1 times x to the negative 2. And you could actually call that negative 1 over x squared if you wanted to. But if you have to take another derivative, if you have to take the second derivative, then I would just leave it in this form because it's a lot easier to keep it. I mean, instead of going from here to here and then back again, just keep it in this form. So the second derivative is negative 2 times negative 1, which is 2, times x to the negative third, and if you had to end there, you'd probably represent it as 2 over x cubed. But let's take the third derivative of that function. The third derivative is negative 3 times 2, which is negative 6x to the negative 4th power, so that would just be equal to negative 6 over x to the 4th. And then we'll just go one more derivative beyond that. We'll take the 4th derivative of this function. The 4th derivative of this function, 6 times 4 is 24x to the negative 5th power, which is positive 24 over x to the 5th. One thing that you might want to start recognizing now is that these coefficients, 1, 2, 6, 24, the next one would be 5 times 24, which is 5 times 4 times 3 times 2. All of these coefficients are actually factorials. So this number 1 here is 1 factorial. This is 2 factorial. 2 factorial is 2 times 1. This is 3 factorial. 3 times 2 times 1. This is 4 factorial. 4 times 3 times 2 times 1. If I did a 5th derivative, it would actually be 5 factorial. 5 times 4 times 3 times 2 times 1. And we could go on, and you could probably start to see a pattern. So whatever derivative we're doing, in this particular example, you would have this match up with this factorial. This is 3 factorial because it is the 3rd derivative. This is 2 factorial, 2nd derivative. So there oftentimes is a pattern when you're taking multiple derivatives. Let's take an example of something that might, oh, I'm out of paper here. Yikes. Let's take another example of something that will stop, and you'll just get all of the rest of the derivatives being equal to something that you'll see. Let's say we have f of x is equal to, let's have it be equal to negative 7x to the fourth plus 2x cubed plus x squared minus 3x plus 1. First derivative, 7 times 4 is 28. 2 times 3 is 6. So hopefully you can get that pretty quickly. The second derivative, let's see, I don't want to make a mistake here. 28 times 3 is 84. This is negative 84. X squared plus 12x plus 2. The third derivative is equal to negative 168x plus 12. The fourth derivative is equal to negative 168. And then if you want to take one more derivative, the fifth derivative is equal to 0 because the derivative of a constant is equal to 0. So any derivative after the fifth derivative, they would all go down to equal to 0. The sixth derivative is equal to 0, and everything after that is equal to 0. So that would actually end at some point in time. Let's take an example of f of x is equal to 2 times the sine of x. The first derivative is 2 times the derivative of the sine of x is cosine of x. The second derivative is 2 times the derivative of cosine is the negative sine of x. So we're going to have to make this whole function negative. The third derivative is negative 2 times the derivative of the sine is the cosine of x. The fourth derivative is negative 2 times the derivative of the cosine, which is the negative sine of x, which actually makes this fourth derivative be positive. And what we have now is that the fourth derivative is actually equal to the very original function that we were given. So if we want to take the fifth derivative, it would be the same as the first. The sixth derivative would be the same as the second. So this would actually cycle around and around and around and just go between two positives and two negatives, two positives and two negatives, and the function would oscillate between sine, cosine, sine, cosine, sine. So this oscillates around, or this cycles through these four values, these four functions, forever. And then I think I'm going to give you one more example, and I haven't shown you this yet, but what if we have f of x is equal to e to the x? I haven't shown you the derivative of e to the x yet, but this is the best function in the whole world because the derivative of e to the x is e to the x, which means the second derivative is e to the x, which means the third derivative is e to the x. So no matter what, any derivative of e to the x is always going to be e to the x. This is the nicest one of all. And if you had a coefficient on the front like a 4 or a 2, that would just keep dropping down through here. But this is a new piece of information for you, is this derivative of e to the x. And I think since you have some homework to do out of your book tonight from page 111 and 112, I think I'm going to end it here. But the only other thing I want to add is because from yesterday, because we were talking about position and velocity and acceleration, I just want to wrap it up with the correlation between yesterday and today's video. I'll say, therefore, the acceleration function is the second derivative of the position function. So how we can say that is if s of t is equal to the position function and s prime of t is equal to the velocity function, then the second derivative of the position function, so you just have the double quotes here, s double prime of t is equal to the acceleration function. And I'm wondering if anybody can look up what the fourth derivative of the position function would be, because that has another name itself, and you might have heard of it before. But I'll just leave you with that question, and I'll see you tomorrow.